By the last week of November, United States Signal Service stations across the northern plains were already logging sub-zero nights and early blizzards. Cattle that had gone into the season with little hay and no shelter would help turn 1886 through 1887 into the big die-up, with some outfits losing half or more of their herds. Most line cabins were small, 4 walls of 8 to 10-inch pine or fir, a roof, a stove, a single 3-foot door cut into the shell once the wall was already standing. Those doors twisted as green logs shrank, jammed under roof load, and leaked heat around crude jambs and thresholds. A few high country builders had begun to reverse the sequence: frame and hang the door on day 1, square and plumb, then stack every log course and roof load to respect that opening. The difference was not heavier walls, but the order of work at 1 3-foot gap. Dawn light filtered through gaps around a doorframe in a cabin 12 miles west of the Belle Fourche River, Dakota Territory, January 1881. Ice crystals lined the underside of roof boards, despite a box stove that had burned through the night. A thin band of daylight showed along the latch edge of the door where the frame had racked out of square. The threshold, cut from scrap timber and spiked directly to the first log course, had heaved with frost, leaving a gap beneath the door bottom wide enough to slide a knife blade through. This was the 4th winter the cabin had stood. The rider who occupied it, a line hand for a ranch running cattle across open range, had already planed the door twice to compensate for settlement and had stuffed fresh moss along the jambs 3 times. The stove consumed nearly a quart of cottonwood every 10 days, half again what a tight cabin should require. The hard winter of 1880 through 1881 tested every structure on the northern plains. United States Signal Service records document sustained cold, minimum temperatures below 0 degrees Fahrenheit for weeks at a stretch, with readings dropping to -20 and lower during clear nights. Snow fell early. The first significant storm arrived October 15, 1880, and continued through March. Wind packed drifts against north and west walls to heights that buried windows and reached eaves. County agricultural reports from the period describe livestock losses, frozen wells, and homesteaders abandoning claims. Ranch records note crews unable to reach stock in critical hours because doors had frozen shut or blown open under wind pressure. One Dakota Territory county reported that of 43 homestead cabins inspected after the spring thaw, 31 showed significant distortion or failure at door and window openings, while only 7 reported structural damage to wall logs or corners themselves. The typical single-pen cabin of the era measured 12 by 14 or 14 by 16 feet. Wall logs ran 8 to 10 inches in diameter, notched at corners with simple saddle joints or V-notches. A single door, roughly 3 feet wide and 6 feet 6 inches tall, provided entry. One small window, often covered with greased paper or a single pane of glass, admitted light. An end chimney of stone or mud and stick construction served a small iron stove or open fireplace. Construction time for such a cabin, with 2 men working, averaged 4 to 6 days. Builders followed a standard sequence visible in period photographs and documented in homestead manuals. Set sill logs on stone piers or directly on graded earth. Raise walls to near full height using notched corners and minimal measurement. Mark door and window locations on the completed shell. Cut openings with axe and crosscut saw. Nail jambs, typically 2 to 3 inch thick planks, often unseasoned, directly to the cut log ends. Build and hang a simple plank door to fit the irregular opening. This approach minimized planning. Layout decisions could be deferred until the shell stood and interior space became visible. Door and window placement adjusted to where logs happened to fall. Jambs and trim covered imprecise cuts. Chinking, moss, clay, or lime mortar mixed with grass sealed gaps between logs and around openings. The method worked adequately in moderate climates or short occupation periods. but it assumed walls would remain stable. Green logs cut in summer and stacked immediately contained high moisture content. As they dried over the first year, logs shrank in diameter by 5 to 10%. A 10-inch log could lose half an inch or more. Across 7 or 8 courses, that accumulated to several inches of vertical settlement. Simultaneously, roof loads, rafters, boards, sod, and accumulated snow compressed the wall, forcing logs tighter together and driving additional moisture out. In a shell, built first and cut later, that movement bore directly on door and window frames. Jambs nailed rigidly to log ends moved with those ends. As logs shrank and settled unevenly, openings distorted from square to parallelogram. Doors that swung freely in August bound tight by December, latches no longer aligned. Gaps opened along jambs as logs pulled away from nailed trim. Cold air infiltrated around all 4 edges of the opening. Remedies required repeated attention. Builders planed door edges to restore clearance. They added shims behind jambs. They rehung doors on relocated hinges. They packed additional chinking around frames. Each fix addressed symptoms without solving the underlying problem. The opening was treated as a decorative cut in a static wall, when in fact it was the intersection of a moving log shell and a rigid rectangular frame. In many documented accounts, the walls remained standing when outfits abandoned a cabin. The trouble almost always began at the 3-foot doorway everyone depended on. A ranch hand stood on frozen ground beside a nearly completed cabin wall, marking a doorway with charcoal on the uppermost log course. Chips and sawdust collected in the snow at his feet as the crosscut saw bit through stacked pine logs. This was standard procedure across the Rocky Mountain and Northern Plains frontier from the 1860s through the 1880s. Build the shell, then cut the openings. The sequence appeared logical. Raising walls required focus on corner notching, keeping courses level, and maintaining plumb. Adding the complexity of door and window layout during that process seemed inefficient. Better to complete the structure, step back, assess interior space and exterior approach, then mark openings where they made most sense. Period carpentry guides and homestead manuals, where they addressed log construction at all, reinforced this pattern. Instructions typically read, raise walls to desired height, mark door and window locations, cut openings square and true, fit frames, and hang doors. The process separated structural work from finished carpentry, allowing different skill sets to operate in sequence. Typical dimensions for a frontier cabin door opening measured 3 feet wide by 6 feet 6 inches high. Some builders cut narrower openings, 2 feet 6 inches, to conserve heat. Others went as wide as 3 feet 6 inches to ease moving furniture or supplies. Height varied from 6 feet to 7 feet, depending on the builder's stature and local practice. Jambs came from whatever dimensional lumber was available: split 2-inch planks, sawn boards from a distant mill, or timber hand-hewn to rough dimensions on site. Green wood was common. Seasoned lumber required advanced planning and storage that few remote builders managed. Jambs were nailed or spiked directly to the cut ends of logs, typically with 8 to 12 large nails per side. No provision for differential movement appeared in most builds. Thresholds received even less attention. A piece of scrap timber, often whatever remained from roof framing, was laid across the bottom of the opening and spiked down to the first or second log course. If the ground was uneven, the threshold might sit directly on dirt, with no drainage provision. This worked adequately in dry climates, but failed quickly where snowmelt or rain pooled at the entry. Door construction followed simple patterns. Vertical planks, typically 1.5 to 2 inches thick, were edge-joined, sometimes tongue and groove, more often simply butted tight. Horizontal or diagonal battens on the interior face held planks together. Strap hinges, either hand-forged locally or purchased from a distant supplier, were surface-mounted with wood screws or clinched nails. A simple latch, wooden bar, thumb latch, or later a manufactured rim lock, completed the assembly. The entire door and frame package, from marking the opening to hanging a functional door, took half a day to a full day, depending on crew size and skill. For most builders, this seemed acceptable. The opening worked even if it required periodic adjustment. But periodic adjustment became constant rework under harsh conditions. Green jambs dried and twisted, pulling nails loose. Logs settling around rigid frames created pinch points at the top and gaps at the bottom. Thresholds on dirt heaved with frost, tilting the entire frame. Doors planned to fit in September bound tight by January as moisture swelled the wood, then shrank again by March, leaving gaps. Ranch foremen's journals and homestead diaries from the 1870s and 1880s contain recurring references to door problems. Rehung cabin door, third time this winter. Planned east jamb again, still binds in morning. Replaced threshold, old one rotted through. These were not catastrophic failures, but they represented ongoing labor costs and discomfort that accumulated over seasons. In regions with severe winters, door failures had direct consequences. A door that jammed shut trapped occupants or prevented quick exit during emergencies. A door that blew open in high wind could not be secured from inside, allowing snow and cold to flood the interior. A poorly sealed door increased fuel consumption measurably. Estimates based on modern infiltration studies suggest that a 1/8 inch gap around a 3 by 7 foot door can increase heating load by 10 to 15% under sustained cold and wind. What most builders treated as a minor carpentry nuisance, planing, shimming, and rehanging, added up to days of lost labor and extra fuel when winters turned severe. A measuring tape stretched across a doorway in an 1870s cabin under study by preservation architects in the late 20th century. The jamb had pulled away from the log ends in 3 places. Patches of newer wood overlapped older, weathered trim. Hinge screw holes showed at least 2 previous mounting locations. The header had sagged nearly an inch at its center, bearing weight it was never designed to carry. This pattern repeated across dozens of surveyed cabins documented in historic American buildings, survey drawings, state historic site reports, and log building preservation briefs compiled from the 1960s onward. Researchers examining 19th century structures consistently found the same distribution of deterioration. Wall fields relatively stable, distortion and repeated repair concentrated at doors and windows. Measured drawings showed walls that remained plumb and square decades after construction. Corner notching, where executed competently, held logs in alignment through settlement and seasonal movement. Chinking between logs, if maintained, continued to seal wall fields effectively. But at openings, the record told a different story. Common documented conditions at door and window frames included cracked and missing daubing around jambs. Jambs pulled away from log ends, creating gaps of 1/2 inch to 2 inches. Crushed or deformed headers bearing roof and wall. Loads, thresholds rotted where set on dirt or inadequately drained bases. Misaligned latches requiring shims or relocated strikes. Added interior storm doors or secondary frames installed after initial construction. And in some cases, entirely relocated openings where original placements had failed beyond repair. One Colorado cabin survey from 1974 described significant racking at the primary entry, with the top of the doorframe displaced 2 1/4 inches laterally relative to the threshold. Wall logs above and below the opening show no corresponding deformation, suggesting the frame moved independently of the shell. Another report from a Wyoming ranch cabin noted 3 distinct generations of threshold timbers, each set slightly higher than the previous, indicating repeated attempts to address drainage and frost heave. The technical cause was straightforward. Log walls, properly notched and chinked, function as semi-flexible assemblies. As moisture content changes and loads apply, individual logs shift slightly relative to their neighbors. The notched corners and compression between courses create a system that accommodates this movement. The wall breathes, not in the sense of air permeability, but in structural tolerance. Door and window openings interrupt this system. They create discontinuities where moving log ends terminate against rigid rectangular frames. If those frames are nailed directly to log ends with no allowance for differential movement, the frame becomes hostage to whatever the cut ends of individual logs do as they dry, compress, and shift. Some logs shrink more than others depending on grain, species, and initial moisture content. Roof loads bear down unevenly. Wind pressure and snow drifts apply lateral forces. The frame, unable to move with the wall, distorts instead. The failure mode was predictable but rarely anticipated during construction. Builders focused on raising walls and completing roofs before weather turned. Door openings were cut quickly to close the shell. Jambs were nailed on to keep wind out. If problems developed later, they could be addressed as maintenance. This reactive approach worked in marginal climates where winters were short and mild. It failed in the severe winter regions of the high plains and mountain west. Preservation architects and log building specialists who studied these patterns during the late 20th century identified the core problem. Openings were treated as subtractive elements, holes cut into a completed wall, rather than as integrated structural components that must be designed to coexist with wall movement. The solution, they noted, lay not in heavier construction or exotic materials, but in sequencing and detailing. Several surviving cabins from the 1880s and 1890s showed a different approach. In these structures, door and window frames were built as independent assemblies, bucks in later technical terminology that sat within but were not rigidly attached to the log shell. Settlement space appeared above headers, gaps of 2 to 3 inches, filled with compressible material and covered by trim. These cabins showed minimal distortion at openings even after a century of service. The record suggested that heavier walls alone did not fix the frontier cabin. Better planning at a single 3-foot gap often made the larger difference. A crude rectangle drawn in pencil on a piece of brown wrapping paper lay weighted with stones on a stump. Arrows indicated prevailing winds from the northwest. A small square marked the proposed door location on the southeast wall, sheltered from direct storm approach and oriented toward morning sun. The date, early fall, 1883, somewhere in the high valleys of the Colorado Rockies. Entrance placement was more than convenience. In deep snow country, doors placed under gable eaves or set back beneath small porches reduced the chance of burial by sliding snow or wind-driven drifts. On open prairie, orientation away from prevailing winter storms, typically northwest, prevented wind from driving directly against the door during blizzards, reducing infiltration and lateral pressure. Period photographs and measured surveys of 19th century mountain cabins show recurring patterns. Trapper cabins and small prospector shelters often featured doors in gable ends, positioned to benefit from eave overhang. Modest porches, sometimes just extended roof rafters supported by posts, created sheltered zones where snow could not pack directly against the door. In some cases, builders added low walls or windbreaks perpendicular to the entry, further deflecting wind. These practices paralleled indigenous building traditions visible in the same regions. Plains earth lodges documented in ethnographic surveys from the late 1800s frequently show entries facing east or southeast, away from prevailing winter winds and toward the warming morning sun. Extended entry tunnels, timber-framed passages extending several feet from the main structure, created airlocks that prevented direct wind penetration and provided space for snow to accumulate without blocking the inner door. Rocky Mountain Ute and Shoshone groups building log or hybrid structures incorporated similar logic. Observers noted that entrances often faced away from the direction of strongest storms and were protected by natural landforms, boulders, ridges, or dense timber that broke wind before it reached the door. The reasons were environmental and practical, not merely cultural. Small trading posts and stage stations built during the same period showed analogous planning. Station records and photographs reveal entries sheltered by porches and positioned to minimize snow accumulation. Doors opened onto cleared approach paths that could be quickly shoveled even in heavy snow. Station agents, responsible for maintaining structures through winter with minimal outside help, had direct incentive to reduce door-related problems. Choosing the door wall early in the planning process fixed multiple downstream decisions. It determined the primary approach path, where people and animals would move most frequently. It set the pattern for snow management, where drifts would form and where they must be cleared. It influenced interior layout, where bunks, stoves, and storage would sit, relative to the entry. And it defined the relationship between the door and the prevailing weather. Once builders began treating door placement as a strategic decision comparable to chimney location, something to plan around, not retrofit into available space, the next step became more intuitive. If the door location mattered enough to sketch it first, perhaps the door itself should be built first. If the entire cabin oriented around a 3-foot opening, perhaps that opening should be the fixed reference point, and the wall should be built to accommodate it rather than the reverse. This shift in thinking was not documented in written form during the 1880s. No builder published a manual explaining door-first sequencing. The practice appears instead in the physical evidence of surviving cabins and in the observable differences between structures that show careful door detailing and those that do not. It spread through direct observation and oral exchange, builder to builder, in regions where winter consequences made the difference visible. When the entrance became part of the weather strategy instead of an afterthought, the next step was obvious. Make the door the first measured element, not the last. 2 vertical posts, a threshold timber, and a header lay across a pair of sawhorses outside a half-built cabin in the Montana high country, late summer 1885. Auger holes and chisel marks showed where mortise and tenon joints had been cut and fitted. The 4 pieces formed a rectangular frame, the skeleton of a door opening, built and squared before any wall log rose above the first course. This assembly, later formalized in log building manuals as an independent buck, represented a fundamental shift in construction logic. Instead of cutting the door opening into a completed wall, the builder created a self-supporting frame designed to stand independently within the log shell. The wall would be built around the frame, not the frame retrofitted into the wall. Dimensions for a typical door, Buck followed practical requirements. Vertical posts ran 3 inches by 6 inches in cross-section, providing adequate bearing surface for hinges and sufficient mass to resist twist and warp. Height matched the desired door height plus threshold thickness and clearance, roughly 6 feet 6 inches to 7 feet from threshold top to header underside. The threshold itself was hewn or sawn flat on top, crowned slightly for water drainage, and left rough on the underside for bearing on stone or sill logs. Width across the inside faces of the posts measured 3 feet to 3 feet 3 inches, allowing a door of standard width plus minimal clearance. The header spanned the opening at the top, connecting the 2 vertical posts. Unlike headers in conventional stud frame construction, the buck header carried no roof or wall load. Its sole function was to support the door weight and provide a rigid connection between the posts. This distinction was critical. By isolating the buck from structural loads, the assembly could remain dimensionally stable even as the log shell around it moved. Joinery mattered. Simple butt joints secured with nails would loosen as the wood seasoned. Proper mortise and tenon or housed shoulder joints, pegged with hardwood dowels, created mechanical connections that tightened under load. The threshold received tenons at both ends that fit into mortises cut into the lower ends of the vertical posts. The header was similarly jointed to the upper ends of the posts. When fully assembled, the buck formed a rigid rectangular frame that could be handled as a single unit. Builders chose dry, straight stock for buck components whenever possible. Using green timber for the buck introduced the same shrinkage problems the buck was intended to solve. Seasoned wood, cut the previous year and stored under cover, remained more stable. In practice, fully seasoned lumber was rare on remote sites, so builders selected the straightest, densest timber available and worked it carefully. The critical operation occurred while the buck sat on sawhorses. A plank door was built and hung on strap hinges attached to the hinge side post. The door was fitted to the opening with the frame under no load, easily accessible from all sides and free of the constraints that would exist once logs stacked around it. Clearances were checked, typically 1/8 to 1/4 inch on the hinge side, slightly more on the latch side to allow for seasonal expansion. The swing was tested, the latch was mounted and adjusted, and the entire assembly was tuned until the door operated smoothly with minimal force. This sequence solved multiple problems at once. It isolated door fitting from wall construction, allowing each to proceed under ideal conditions. It established the opening geometry precisely before logs began stacking, preventing accumulated errors, and it created a mechanical system, hinges, latch, frame, that could be tested and verified before being committed to the structure. If the door did not swing and latch perfectly while the buck sat on the sawhorses, nothing else proceeded. Flat stones set into graded earth marked the base of a door opening before the first full log course was in place. The largest stone, roughly 12 inches square and 3 inches thick, sat directly beneath where the hinge side jamb would stand. A second, slightly smaller stone supported the latch side. Between them, a shallow trench held a timber threshold, sloped gently outward to shed water. Foundation detailing at the door opening determined long-term stability as much as any other single factor. The hinge side bore the majority of door weight. A solid plank door could weigh 60 to 80 pounds, plus the dynamic loads of repeated opening and closing. That force concentrated on the bottom hinge, which transferred it through the jamb into whatever supported the base of the frame. If that support was inconsistent, dirt in one area, a stone pad in another, the frame would settle unevenly, throwing the door out of plumb. Builders addressing this problem placed continuous bearing under the hinge side post. A flat stone pad extended to the first sill log or the threshold timber itself, creating an uninterrupted load path from hinge to ground. The latch side, carrying less load, could use a smaller pad or accept minor adjustment through shims placed later. Threshold design deserved equal attention. A timber laid directly on dirt-absorbed ground moisture, promoting rot. Frost heaved during winter lifted unsupported thresholds, tilting the entire door frame. Standing water from snowmelt or rain soaked into end grain, accelerating decay. Within 2 or 3 seasons, thresholds set without proper bearing and drainage often required replacement. The solution combined elevation and drainage. The threshold was set on stone pads or short post footings that raised it 2 to 4 inches above grade. The top surface was crowned slightly, a 1/4 inch rise at the center of a 3-foot span, so water ran to the edges rather than pooling in the middle. The underside remained rough or was notched to key into the stone supports, preventing lateral movement, and the threshold extended slightly beyond the door opening on both sides, creating small ledges where water could drip free rather than running back along the sill. With the foundation prepared, the door buck was stood upright and positioned. Temporary diagonal braces held it plumb in both directions, parallel to the door plane and perpendicular to it. A plumb bob checked the hinge side post, the most critical element. Even a 1-degree lean at the bottom of a 7-foot post translated to more than 1.5 inches of offset at the top, enough to bind the door or create a wedge-shaped gap that could not be sealed. Once plumb, the buck was anchored to the first log course and sill timbers. The method of attachment varied depending on builder preference and available materials. Some used wooden pegs driven through the lower buck posts into the sill logs. Others employed simple iron brackets. The goal was not rigid fixation, but stable positioning. The buck must stay plumb and square, but it must also be able to slide vertically relative to the log shell as settlement occurred. This required builders to think several months ahead. The wall, once loaded with roof and snow, would compress. The buck, isolated from that load, would not. The connection between them must allow relative motion. Achieving this with hand tools and improvised fasteners required care and judgment, not advanced engineering, but it did require recognizing the problem before the build, not after the door jammed. A 1-degree lean in a 6.5-foot jam could shift the top of the door more than 1 inch, more than enough to stick under snow load. A tapered wooden wedge sat in a gap above a door header, visible from inside the cabin, but hidden beneath exterior trim. Dry moss packed the remaining space. The gap measured 2.5 inches at the time of construction, late summer 1884, a ranch cabin on a tributary of the Powder River in northern Wyoming. By the following summer, the wedge had been tapped out 1/2 inch as the wall settled, and by the second winter it was removed entirely, leaving only the moss to fill a gap now compressed to just over 1 inch. This small void represented one of the most important details in door-first construction, planned settlement space. Green log walls, even when built with care, did not remain static. As timber lost moisture and fibers compressed under load, the overall height of the wall decreased. The amount of movement depended on log size, species, initial moisture content, and the magnitude of roof and snow loads, but it was always measurable, typically 1 to 3 inches over the full height of a 7 or 8-foot wall. If the door buck was rigidly connected to both the foundation below and the wall logs above, that settlement would crush the frame, distorting the opening and binding the door. The solution was to isolate the buck from downward-moving wall loads by leaving a compressible gap above the header. In practice, this gap was built in stages. During initial construction, the space above the door header was left open. No log course touched the header itself. The first wall log above the opening spanned across the top of the door, bearing on logs to either side, but not on the header. Temporary puncheon boards or wooden wedges were placed in the gap to carry minimal load and prevent debris from falling through. Dry moss, wool, sawdust, or other compressible material filled the remaining space. As the roof went on and the first winter snows accumulated, the wall began to settle. The wedges compressed or were periodically tapped out to allow continued movement. By the end of the first full year, most of the settlement had occurred, and the gap above the header had closed to a stable dimension, often 1 inch or less. At that point, permanent trim could be installed to cover the gap, or it could be left as ongoing settlement space for future adjustment. This detail appeared in various forms across surviving cabins from the 1880s and 1890s. Some builders used slip joints, vertical slots in the buck posts through which fasteners passed, allowing the wall to slide downward relative to the frame. Others employed settling, boards, horizontal planks stacked above the header that could be removed one by one as settlement occurred, progressively lowering the wall onto the frame in a controlled manner. Still others simply left the gap open and filled it loosely, relying on regular maintenance to adjust packing as needed. The principle remained consistent. The door frame must not carry wall or roof loads. It must support only the door itself and remain dimensionally stable while the shell around it moves. The few inches of planned emptiness above the header, easily overlooked or dismissed as sloppy workmanship by observers unfamiliar with log construction, were in fact deliberate engineering. Modern log building standards codify this practice explicitly, specifying settlement allowances above all door and window openings and detailing methods for achieving them. The underlying logic traces directly to field solutions developed on the frontier, where builders learned through repeated failure that treating openings as rigid, load-bearing elements guaranteed distortion. The extra inches of planned emptiness above a header often did more for long-term door function than several inches of extra wall thickness. Charcoal marks on a scrap plank nailed to a cabin's exterior showed a rough schedule. Day 1, sills and door. Day 2, walls to window. Day 3, walls to plate. Day 4, roof. Day 5, floor and chink. Day 6, adjust. The board remained in place after construction, a working artifact of sequencing discipline. The cabin stood on a small ranch in the South Platte drainage of Colorado, completed in 6 days during late August 1886 by a crew of 3. This schedule illustrated door-first building compressed into a typical frontier time frame. Most small cabins took 4 to 7 days to construct with a small crew. Adding door-first sequencing did not significantly extend that window. It redistributed labor within it. Day 1 began with foundation and sill work. Flat stones were set at corners and midpoints. Sill logs were leveled and squared. Then, before any wall log went up, the door buck was assembled on sawhorses. The door was hung, and the entire assembly was tuned until it operated smoothly. The buck was then stood on prepared stone pads, braced plumb in both directions, and anchored to the sill logs. The first full log course was notched and set, with logs on either side of the door carefully scribed to maintain proper clearance from the buck. At the end of Day 1, the only vertical element rising above knee height was a braced door standing in open air, swinging freely. Day 2 focused on raising walls. Logs were notched at corners and set in sequence. Each course that intersected the door opening received extra attention. Measurements were checked against the buck, clearances verified, and the door swing tested after every 1 or 2 courses. If a log bowed inward and encroached on the door space, it was rejected or planed before. Setting. This iterative checking ensured that no accumulated error went unnoticed until the wall was complete. By the end of Day 2, walls stood 3 to 4 courses high, roughly waist level, and the door remained freely operable within its frame. Day 3 brought walls to full height. Logs continued up to the plate, typically 7 to 8 feet above the foundation. A window buck, if included, was set and braced, using the door head height as a reference datum. Settlement space was left above the door header and packed with compressible material. The crew rechecked the door swing after setting the final wall course. By evening, the shell was complete and the door still functioned. Day 4 covered the structure. Plate logs went on, rafters were notched and set, and primary roofing, split boards or shakes, covered the span. With the door now under shelter, risk of rain damage during subsequent interior work dropped. The door itself, having been exposed since Day 1, showed whether its construction was sound. If it had swollen, bound, or warped during several days of weather exposure, those problems appeared now, while they could still be addressed with full access to the frame. Day 5 dealt with interior finish. Puncheon floor planks or split logs were laid, cutting cleanly to the threshold already in place. Primary chinking around log joints was applied, with special attention to the edges where wall logs met the door buck. The goal was not perfect sealing on the first pass, chinking required repeated maintenance, but establishing a baseline that would reduce immediate drafts. Day 6 was reserved for final adjustments. Hardware was tightened. Interior door stops and exterior storm boards were added, if materials allowed. The door swing and latch alignment were checked under full shell and roof load. Minor planing or shimming corrected any issues that appeared as the structure settled into its initial configuration. At the end of Day 6, the crew left a cabin whose only moving part had been working since Day 1 and had been tested under every stage of increasing load. In most builds, the door was the last thing to work properly. In this sequence, it was working before the second course and never stopped. A page from a ranch foreman's account book, winter 1885 through 1886, showed 2 columns tracking firewood consumption at 2 line camps of similar size. Camp A, with a door installed after wall completion, burned 43 cords of cottonwood between November and March. Camp B, with a door-first buck and careful settlement detailing, burned 37 cords over the same period. The difference? 6 cords, representing roughly 6 days of cutting and hauling labor, was noted in pencil at the bottom of the page. This was a moderate winter by Northern Plains standards. Temperatures dropped below 0 Fahrenheit on multiple occasions, but did not sustain extreme cold for weeks at a stretch. Snow accumulated but did not bury structures. Both cabins faced similar exposure and housed riders with similar heating preferences. The structural difference lay entirely in how the door and opening were detailed. Fuel consumption provided a measurable proxy for door performance. A door that fit poorly, gaps around the frame, binding that prevented full closure, or distortion that created wedge-shaped openings allowed cold air to infiltrate. That infiltration increased the heating load. The stove had to burn hotter and more continuously to maintain interior temperature. Over a 5-month winter, small differences in infiltration accumulated into significant differences in fuel consumption. Modern building science quantifies this relationship. For a small, single-room structure with minimal insulation, infiltration around a 3 by 7 foot door opening can account for 15 to 25% of total heat loss under windy conditions. A gap averaging 1/8 inch around the perimeter, easily achieved by a door that has settled out of square, translates to an effective opening area of roughly 4 square inches. Under a 20-mile-per-hour wind at 20 degrees Fahrenheit below zero, that gap exchanges interior and exterior air rapidly enough to require an additional 10 to 15% fuel input to maintain 70 degrees Fahrenheit inside. 6 cords of wood over a 5-month winter represented approximately 1 cord per 3 weeks of additional fuel consumption. At 1/2 cord per man-day of cutting and hauling labor, a reasonable estimate for cottonwood, in moderately accessible stands, the 6-cord difference equaled 12 man-days of work avoided. For a 2-man line camp, that was 6 days per man, or roughly 1 day per month, saved by better door detailing. The foreman's notation suggested this difference had been observed and quantified. Whether the crew understood the specific mechanism, infiltration driving heat loss, or simply noticed that one cabin stayed warmer and used less wood is unclear from the record. What mattered was the pattern. Cabins with carefully detailed doors consistently outperformed cabins with doors retrofitted into completed shells. Fuel savings were not the only advantage, though they were the most easily documented. Time savings from avoided rework, rehanging doors, planing edges, adjusting latches were harder to quantify, but no less real. A door that required attention once per season versus once per month represented several hours of labor saved, multiplied by however many months the cabin remained occupied. In regions where line camps were scattered across vast ranges and riders worked alone or in pairs, those hours had strategic value. Time spent fixing a stuck door was time not spent checking stock, repairing fence, or riding to assist neighbors during emergencies. Every trip back to a camp to address a door problem consumed a day. Riding in, executing the repair, and riding out. A door that worked reliably from day one eliminated that entire category of maintenance travel. The economics of door-first sequencing thus involved a modest upfront investment, several additional hours during the build to assemble and tune the buck, set foundation pads, and check alignment through each wall course in exchange for compounding returns over time. Lower fuel consumption each month, fewer repairs each season, and reduced travel each year. When calculated across multiple cabins in an outfit's line camp network, the cumulative savings became significant. An operation running 6 to 10 small cabins across its range could avoid dozens of maintenance trips and save tens of cords of fuel annually by standardizing door-first construction for all new builds and major reconstructions. What looked like extra fuss around one 3-foot opening often returned itself in a single bad month of saved repair trips and wood piles. 3 architectural drawings lay side by side on a surveyor's table: a ranch line cabin from 1878, a trading post structure from 1882, and a United States Forest Service patrol cabin from 1908. Different builders, different decades, different purposes, yet all 3 showed gable-end doors under extended eaves, independent door frames, and visible settlement space above headers. This convergence was not coincidence. It represented parallel evolution driven by shared selection pressure. All 3 structures were designed for winter occupancy in harsh climates where door failure carried immediate consequences. Ranch line cabins served as outposts for riders checking cattle across open range during winter months. Crews of 1 or 2 men occupied these cabins for weeks at a time, often in severe cold, with limited ability to call for help or evacuate to a main ranch. A door that failed, jammed shut, blown open, or so poorly sealed that the interior became uninhabitable could strand riders or force them to abandon the cabin and attempt a dangerous winter ride to the next shelter. Ranch foremen who managed line camp construction developed practical standards through experience. Cabins that followed certain patterns, doors and gable ends, sheltered entries, independent frames, required less maintenance and fewer emergency repairs. Those patterns spread informally. Foremen moved between outfits, carrying their building preferences with them. Riders who had suffered in poorly built cabins described what failed when they helped construct new ones, and ranchers visiting each other's operations observed and copied successful designs. Trading posts operated under similar constraints. A post in remote mountain or plains territory might see significant winter traffic: trappers bringing furs, indigenous groups trading goods, travelers seeking shelter during storms. The entry had to function reliably under constant use, in all weather, with minimal opportunity for repair. Posts that developed door problems lost business and gained reputations as poorly maintained operations. Account books and correspondence from trading posts occasionally mentioned door maintenance, usually in the context of seasonal preparation. Repaired main door and reinforced threshold before winter trade appeared in an 1881 letter from a post operator in Montana Territory. New door frame installed with proper clearance above, old frame crushed by settling, showed up in an 1885 expense ledger. These fragments suggested that post operators learned the same lessons as ranch foremen, often through similar failures. Forest Service and Park Patrol cabins, built beginning in the late 1890s and early 1900s, codified what earlier builders had learned through trial and error. The Forest Service, managing vast areas of timber and grazing land, needed small, durable cabins at strategic points where rangers could stay during winter patrols. These cabins had to survive years of seasonal use with minimal supervision, remain habitable during storms, and require as little maintenance as possible. Early Forest Service construction standards, visible in archived drawings and specifications, explicitly addressed door and window detailing. Doors were to be framed independently of the log shell with adequate settlement allowance above. Thresholds were to be set on solid bearing and sloped for drainage. Hinges were to be of sufficient length and strength to support door weight through repeated freeze-thaw cycles. These written standards captured in formal language the field knowledge accumulated by frontier builders over the previous half-century. The physical evidence showed where institutional memory had absorbed craft practice. Measured drawings of early patrol cabins revealed doors treated as primary structural elements rather than afterthoughts. Gable-end placement appeared consistently, sheltering entries beneath eaves. Small porches or extended roof lines were standard features. Settlement gaps above headers were dimensioned on plans, not left to chance. Independent bucks, though not always called by that name, appeared in section drawings. The progression from improvised frontier cabin to standardized government structure traced a learning curve. Early homestead cabins, built by individuals with limited time and resources, often showed minimal door detailing. Ranch-line cabins, built by outfits with repeated winter experience, showed improved door practices. Trading posts, needing year-round reliability, refined those practices further. And government patrol cabins, drawing on decades of accumulated field experience, codified the patterns into reproducible standards. The more a cabin was expected to face snow and wind, the more its drawings read as if the door, not the wall, was the main engineering problem. A simple sketch showed a cabin in cross-section, stacked logs forming walls, a door, buck standing within the shell, and snow piled halfway up the exterior. Arrows indicated vertical settlement of logs under roof load and horizontal pressure from accumulated snow pushing against the door. The diagram appeared in a preservation brief explaining common failure modes in historic log cabins, but it could have been drawn from field observations in the 1880s. Doors faced combined vertical and lateral loads during severe winters. Vertical loads came from wall settlement, logs compressing and shrinking as moisture left and roof weight bore down. Lateral loads came from wind pressure and, more significantly, from snow drifting against walls and doors. A drift packed solid by wind could exert substantial horizontal force, enough to distort frames or push doors inward if the structure lacked strength or proper bracing. Shell-first construction, where door frames were nailed directly to log ends with no settlement allowance, handled these loads poorly. As the wall settled, logs above the door bore down on the header. If the header was undersized or the frame was not designed to carry load, the header crushed or bent. Even a quarter-inch of deformation at the header was enough to bind a door that had previously swung freely. The binding typically occurred at the top corners, the latch side top corner in particular, where the geometry of door swing amplified small header movements into significant interference. Lateral loads from snow added complexity. A door frame nailed rigidly to log ends moved with those ends as snow pressure deformed the wall. Logs, being relatively flexible, could bow inward slightly under lateral load without structural failure. But a door frame, being a rigid rectangle, could not bow without racking. The frame shifted from square to parallelogram, throwing the door out of alignment. Hinges designed to operate in a square frame bound when the frame racked. Latches no longer met their strikes. Gaps opened on one side, while the opposite side jammed tight. Door-first construction with independent bucks and settlement space addressed both load types. The buck, anchored to the foundation, but not rigidly attached to the log shell, remained square even as logs around it moved. Settlement space above the header prevented downward-moving wall loads from bearing on the frame. And the buck's connection to the foundation, whether through stone pads, sill logs, or minimal fasteners designed to allow vertical sliding, kept it stationary while the log shell compressed around it. Lateral loads from snow were resisted primarily by the mass and stiffness of the buck itself. A properly dimensioned buck, 3 by 6 inch posts joined with mortise and tenon, had enough rigidity to resist snow pressure without deforming. The log shell, meanwhile, could flex slightly without transferring that flex to the rigid frame within it. The system worked because the two elements, flexible log shell and rigid door frame, were decoupled, each free to respond to loads independently. Failure documentation supported this analysis. Preservation architects examining collapsed or severely deteriorated cabins consistently found that doors and windows failed before structural elements. Wall corners remained intact, roof framing stayed sound, but door frames showed crushing, racking, or complete detachment from the shell. The pattern suggested that openings were the weak link, not because they were inherently fragile, but because they were detailed without consideration for how the building would move under load. Cold added its own complications. Wood, like most materials, contracted as temperature dropped and expanded as temperature rose. A door built in summer and hung in a frame at 70 degrees Fahrenheit would shrink when exposed to winter temperatures of 0 or below, creating gaps that had not existed during installation. Conversely, a door exposed to moisture from snow or rain and then taken into a warm interior would swell, sometimes enough to jam tight in an opening that had provided adequate clearance when dry. Builders aware of these behaviors left slightly more clearance on the latch side, an extra eighth to quarter inch, and ensured the hinge side was perfectly plumb and solidly mounted. The hinge side, being the pivot, had to remain stable. The latch side, where the door closed, could tolerate minor seasonal adjustment through shims or biplaning the door edge. The worst winters did not create new problems. They merely finished what indifferent detailing at the doorway had already started. A single sentence in the International Code Council's standard for log structures read, "Provide settlement space above all door and window openings. Use independent bucks anchored to the subfloor, not the log wall." The language was technical, bureaucratic, and unremarkable to anyone familiar with modern log home construction. But it codified, in mandatory form, principles that frontier builders had worked out through experiment and failure more than a century earlier. The path from field practice to written standard was long and indirect. Frontier builders in the 1880s and 1890s had no engineering literature to consult for log construction. Pattern books of the era addressed stud frame houses, masonry, and occasionally timber frame structures. But log cabins were considered too simple and too regional to warrant formal documentation. Builders learned from direct observation, from oral instruction by more experienced hands, or through their own trial and error. As log construction transitioned from frontier necessity to recreational choice, vacation cabins, hunting lodges, and later full-time homes built for aesthetic or lifestyle reasons, demand grew for technical guidance. In the mid-20th century, log home manufacturers and specialty builders began publishing construction manuals. These early manuals, written by practitioners rather than engineers, documented field-tested methods for dealing with log movement, settlement, and structural behavior. One recurring topic in these manuals was openings. Every author who addressed log construction at length devoted significant attention to doors and windows, describing independent frames, settlement gaps, and methods for anchoring bucks without constraining wall movement. The language and diagrams varied, but the core message remained consistent. Treat openings as systems that must coexist with, not resist, the natural movement of log walls. By the late 20th century, log construction had become common enough to warrant formal engineering analysis and code development. The International Code Council, working with log home industry associations, developed ICC 400, a standard specifically for log structures. That standard, first published in 2003 and updated periodically, included detailed provisions for settlement management, opening design, and fastening methods. The settlement space requirement, 2 to 3 inches of compressible gap above all door and window headers, appeared explicitly. The independent buck, though not universally mandated, was described as the preferred method for achieving proper settlement behavior. Anchoring methods were specified. Bucks were to be fastened to subfloors or foundations, not to log walls, and any connections to wall logs were to allow vertical sliding through slotted holes or similar details. These provisions applied to all log structures covered by the code, regardless of size or occupancy type. A builder constructing a small cabin in the mountains of Montana was required to follow the same settlement detailing that a builder erecting a large log home in Colorado followed. The standard made no distinction based on climate severity, though it acknowledged that settlement magnitude varied with log moisture content and species. The logic embedded in the code was unchanged from what frontier builders had discovered, controlling the opening and allowing the wall to move around it, produced better long-term performance than trying to integrate openings into a rigid shell. The language was different: settlement space, independent buck, slip joint fastening. But the underlying principle was identical. Reading the standard, a builder from the 1880s might not recognize the terminology, but would recognize the intent. The settlement gap was the same compressible space they had packed with moss or wool above door headers. The independent buck was the same freestanding frame they had built on sawhorses and hung the door on before raising walls. The slip joint fasteners were a more refined version of the loose pegs or brackets they had used to keep the buck plumb without locking it to settling logs. In this way, formal codes acknowledged what field practice had already proven. The written standard did not create new knowledge; it ratified old knowledge, making it accessible to builders who lacked direct experience with log construction or access to oral instruction from experienced hands. The formal language of modern codes was a belated acknowledgment of what field practice had already proven. The door was a structural problem, not just a carpentry detail. A single line in a ranch foreman's ledger, dated April 1891, read, "Line camp cabins, 3 rebuilt this season using doorbuck method. Winter fuel consumption down approximately 18% versus prior years. No mid-season repairs required." The entry appeared unremarkable among tallies of hay purchased, fence materials used, and cattle losses recorded. But it summarized 5 years of incremental learning compressed into a few construction decisions and translated into measurable operational savings. The numbers sketched a picture. 3 cabins rebuilt meant approximately 18 to 20 days of crew labor, 6 to 7 days per cabin. That labor was not additional cost. It was time that would have been spent building cabins anyway, simply redirected into different sequencing. Building doorbucks and setting them first added perhaps half a day per cabin compared to shell-first methods, a modest overhead easily offset by time saved later. Winter fuel consumption down 18% translated to real quantities. If a typical line cabin burned 25 to 30 cords of cottonwood over a 5-month winter, an 18% reduction saved 4 to 5 cords per cabin. Across 3 cabins, that totaled 12 to 15 cords, not cut, not hauled, and not burned. At half a cord per man-day of work, that represented 24 to 30 man-days of labor avoided, more than the entire labor investment in all 3 rebuilds. No mid-season repairs meant 0 trips to address stuck doors, failed latches, or blown open entries during winter. Each such trip, for a line camp 10 or 15 miles from the main ranch, consumed a full day, saddling up, riding out, executing the repair, and riding back. Over previous winters, the foreman's ledger showed multiple such trips per cabin. Eliminating them saved not just time but also risk. Winter travel across open range in storms or severe cold carried inherent danger. The indirect benefits were harder to quantify, but no less real. Riders living in cabins that stayed warmer and required less constant fire tending could focus more attention on stock. Doors that opened and closed reliably allowed faster response when cattle drifted or needed checking during storms. Entries that did not jam or blow open preserved interior conditions, dry tack, secure food storage, habitable sleeping space that affected rider health and effectiveness. From an economic standpoint, the investment in door-first construction paid for itself within a single winter and continued returning benefits for as long as the cabin stood. The arithmetic was stark enough that outfits with institutional memory, ranches run by the same families for decades, operations with experienced foremen who tracked costs closely, adopted the practices quickly once they became aware of them. Outfits without that continuity, or with high turnover in leadership and crews, often continued building shell-first cabins by habit, suffering the same problems and costs repeatedly. The spread of door-first practices across the northern ranges during the 1880s and 1890s was not documented in formal publications or articles. It occurred through direct observation and informal exchange. A writer who had worked on one outfit took his knowledge to the next. A ranch owner visiting a neighbor's operation saw how line cabins were detailed and asked questions. A foreman hired from outside the region brought building methods from his previous employer. Knowledge moved through social and professional networks carried by people who had seen the difference firsthand. By the late 1890s, door-first sequencing and independent bucks were common enough in some regions to be considered standard practice rather than innovation. A builder asked to construct a line cabin in Wyoming or Montana would, more often than not, begin with the door unless specifically instructed otherwise. The method had become naturalized into the craft tradition, its origins forgotten or no longer discussed. On the northern ranges, survival in a hard winter often depended less on heavy walls than on how early someone squared, hung, and trusted a single 3-foot door.